good afternoon, good evening, everybody, wherever your time zone may place you. It's a real pleasure to be with you today, and I look forward to spending quality time with you to talk about one of my favorite topics, namely instrumental variables analysis and causal inference from observational data. We have a lot of ground to cover. You've received the slides, of course. There's 285 slides in this deck. I'm gonna give you a real hint up front. We will not cover all of these slides, but since I occasionally give talks on more specialized topics that have to do with instrumental variables analysis, I think it's just right and proper to share these slides with you since I have them, even if we won't cover them all. This also affords us a measure of flexibility because on the third day, we'll be able to prioritize your interests, and I'll simply ask you what topics you want some greater depth in or others. So what are we meeting about? We're meeting about instrumental variables analysis. At the front of your slide deck, and I believe you can see my slides now. Thank you. At the front of my slide deck, there are some recommended readings. Instrumental variables analysis is covered in really any good econometric textbook and in a few non-economics textbooks. Here are three textbooks that I really like. Angrist and Pishka's Mostly Harmless Econometrics, which is, sort of the MA level Bible of applied microeconomics still. There's a distinctly more technical book by Chuck Mansky, who also covers instrumental variables analysis. If you open that book, you'll be surprised because this book only has maybe 10 pages on IV. Now, Mansky is extremely efficient and just thinks that anything that needs to be said can be said in 10 pages. My experience is that one needs a few years of training before one can appreciate the awesome conciseness of that presentation. So the Mansky book is perhaps not the first stop. And then, we have a traditional econometric textbook. This is, I think, very much the, if you will, the holy text for required graduate level econometrics courses by Jeff Wooldridge. And this has copious amounts of highly technical detail. And my goal is that this course will help those of you who are not economists, and I believe that's almost all of you, to go beyond the basics of instrumental variables analysis, to develop deep intuitions and a clear understanding of the underlying mechanics, so that after this course, you can go to the Wooldridge book, look at all that math and be like, oh, okay, I know what he's talking about, and get into the details and the specialized topics that are of interest to you. That said, other disciplines do instrumental variables too, and I'm very pleased really to have observed over the last 10, 15 years that IV has migrated from economics into observational epidemiology, population health, certainly to political science, and to an extent into sociology. Now, these are just the disciplines that I, work in, dabble in, perhaps. There are other disciplines in the social sciences that don't do as much IV. For example, in psychology, it's rarely seen. But the day is young, and we can advance. For sociologists, I recommend Morgan and Winship. For political scientists and those who really don't want to see any math, I recommend Thad Dunning's book, which is a marvel of conveying deep intuitions. Educational researchers will love Murnane and Willett. And then, of course, for the computer scientists, Yuda Pearl's classic text on directed acyclic graphs also has a small chapter on graphical identification criterion for IV, which we'll cover briefly. There are Stata books. We're going to work in Stata. Here's a glossary in case I neglect to define or repeat acronyms, but I will do my best not to fall into, technical abbreviations and sort of in-group language. If I do that, if I sort of suddenly start talking like somebody who's really high on technical language, just call me out to make sure that I'm that I use clearer language, which is very much my goal in this course. Now, all that said, let's get into the weeds. Let's get into the details. Let's start with some motivation. Now, you have your reasons to be in this course. I want to make sure that we're on the same page. Here are the kinds of questions that I want us to keep in mind. Real life social and biomedical science questions. These are the questions that I think are good questions that will motivate spending some time with statistics. So wouldn't it be nice? Wouldn't it be nice to have some answers for a change on these important questions? Is military service an engine of economic mobility? Does an educational year of schooling pay off in the labor market? What good are randomized trials when patients refuse their treatment? And perhaps most important of all, now that we're going into holiday season, does my weight gain affect your weight? Each of these questions has shelf meters, cubic feet of literature associated with it. Each of these topics is actually quite contested empirically. Each of these topics has one thing in common. They are all causal questions. Now, causal questions are questions that can be formalized within the potential outcomes framework of causality. This is the framework in which I operate, but fortunately, not just I, because that would be creepy if I just told you my own special way of doing things. No, the potential outcomes framework is the reigning, the dominant, pretty much the only framework of causal inference used in the social and biomedical sciences today. It was developed in statistics. It's now dominant in economics and also in the other social and biomedical sciences. Now, this is not a course on the potential outcomes framework. However, I want to assure those of you who are familiar with it that everything we do is consistent and can be operationalized within the potential outcomes framework. For those of you who are not familiar with the potential outcomes framework, let me just tell you what's important about it. What's important about it is that the potential outcomes framework operationalizes causal effects as answers to what-if questions. So we ask, how would my outcome be different if I had received treatment rather than control? Okay, so that's one of the reasons the potential outcome framework is so popular, is that this captures most everybody's intuition of what a causal question, a causal answer is supposed to be. A causal question is a causal effect is an answer to a what-if question that compares two counterfactual states of the world where I've taken treatment versus the world where, possibly contrary to fact, I did not take treatment. And then we just compare my outcome across these two worlds in order to figure out what the causal effect of taking versus not taking the treatment would have been. Now, formally, we define causal effects as differences between so-called potential outcomes. So a causal effect then is the difference between the potential outcome that would have obtained if I had received treatment versus the potential outcome that would have obtained if, possibly contrary to fact, I had received control. Now we could slap notation on it, but I'm not going to do that until the third day. Okay, this just settles what we're after, causal effects. We want to know what would happen if I received treatment rather than control. Now, answering such questions is, of course, really difficult. The problem is that observed correlations rarely answer causal questions because observed correlations are confounded by both observed and unobserved factors. Let's get back to our running examples. We asked, is military service an engine of economic mobility? It's hard to say. We can't just compare those who've served in the military to those who've not served in the military, because that's like apples and oranges. Military service is highly selected of typically unobserved characteristics of individuals, such as physical and mental health. Okay, so simply observing that those who once were in the military have different wages than those who have not been in the military really tells us nothing about the effect of military service and outcomes, because we're comparing apples and oranges. Now, the same general problem applies to the other examples. Right? So here's a question that perhaps some of us have asked ourselves at some point as we were staying in school and then staying another year in school. Does an additional year of schooling actually pay off in the labor market? Does it increase chances of employment? Does it increase wages? Now, those of us who are in academia, yeah, that's what we're telling ourselves and our students usually, though, the truth is getting a PhD is not an economically rational choice in most fields. But so that begs the question, right? Is another year, does that pay off in the labor market? Well, it's really hard to say. We can't just compare the wages of those who have 16 years of education to those who have 8 years of education, because these people in these two groups are not comparable. Okay, schooling and wages are both highly selective of things such as unobserved ability and lots of other things. So again, apples and oranges. We can't just compare these outcomes. Third, what good are randomized trials if patients refuse their treatment? Hard to say, right? The beauty of a randomized trial is that randomization creates comparable groups. Treatment and control group, by virtue of randomization, will be comparable on average. So we can compare their outcomes and get a causal effect. But if people refuse their assignment, then they often have their reasons to do so. Perhaps the drug under investigation has side effects, and those who are most vulnerable to the side effects drop out. Now, maybe vulnerability to side effects also is a risk factor for adverse health outcomes. So now suddenly you have a treatment group that's comprised of comparatively more healthy people than the control group. In other words, if you have selective dropout from a randomized trial, the trial ceases to be a randomized controlled trial and simply becomes an observational study with self-selection into treatment. So again, the observed correlation is not informative of a causal effect. Now, finally, does my weight gain affect your weight? Again, we can't just compare, right? Because birds of a feather sing together. It could simply be that, the kinds of people that find themselves in a room together, in a room that's dedicated to instrumental variables analysis, it could just be that these people are similar in in unobserved ways so that, my phenotype is going to be correlated with your phenotype, even though my weight gain has not actually caused anything about your weight. Good, it's all very difficult. Now, enter instrumental variables analysis. Instrumental variables analysis can be used for various things. But primarily, it's a method to extract causal information from observational, non-experimental data with unobserved confounding. So IV is a way to take an observed association that's not informative of causality, massage it in a principled and clever way in order to strip away all the causal junk, all the correlational associational junk in that association to reveal the causal core. So here are the steps that we're going to do. Our goal in this course is to estimate the causal effect of one or more treatments, which I usually call T, on an outcome that I usually call Y. Now, the problem in observational data is that treatments may be correlated with the so-called error term in the structural equation, perhaps because there's omitted variable bias or because there's measurement error. If that's the case, then our standard regression tools will not be able to recover the causal effect of T on Y. So what's the solution? The solution is to exploit so-called exogenous variation, as if random variation in the treatment, using a so-called instrumental variable in order to reconstruct a randomized experiment within the observational study. That's why we call instrumental variables analysis a quasi-experimental approach. Now, I'll explain all of these terms, of course, in that course, right? This is just a grand promise for the next 3 days. What do we gain from this? Well, we reap the reward that if we can use instrumental variables analysis, if the conditions are right, then instrumental variables analysis allows us to make more defensible causal claims. But nothing in this fair life is free, so we have to pay a price. And the price is that we have to make different untestable assumptions about the data generating process. And to add insult to injury, we have to contend with really large standard errors. But hey, nothing is free. We're in a situation where regression won't work. So we abandon the regression assumptions. Instead, we make the IV assumptions in order to get something out of a really difficult situation. We pay a price for that. We have to still make assumptions, and we're going to get, high variance in our estimators. But still, we can make more defensible claims. Now, as a rule, IV estimators have these 3 properties. First, IV estimators are actually mean biased in small samples. That's different from OLS. OLS is, under the OLS assumptions, unbiased in samples of any size. IV is not. Second, IV has really large standard errors, like 1, 2, 3 orders of magnitude larger than the corresponding OLS estimate. So we'll have to pay some attention to getting the standard errors right, even in large samples. And third, IV estimators are consistent. Now, consistency means that under maintained assumptions, as sample size gets really large, the estimate gets ever more precise, so that in an infinitely large sample, IV is guaranteed to give us an estimate that coincides exactly with the true effect. Hence, consistency is the selling point for instrumental variables. Now, since small sample theory for IV is complicated and you might say less well developed, we'll deal with it only in passing. Instead, this course will focus on large sample properties of the IV estimator because we want to be in a situation where we can exploit the consistency of the IV estimator. That said, I will not bother you with formal asymptotics. This is not the course for that, right? Indeed, I will try to be as non-mathy as possible, because I'm assuming that you're empiricists like me. You're people who want to get information from real data rather than, reveling in the glory of mathematical properties of these estimators. David, yes, please. Good to see you, David. I can't hear you. Okay, I think you're muted, David. Please unmute yourself.
For high variance, you said 2 or 3 orders of magnitude, not 2 or 3 times?
Orders of magnitude, that's right.
Okay. And then when you say it's mean biased in small samples, I don't understand what mean bias is.
Okay. So mean bias is what most people mean by bias. So bias means that on average, over repeated samples, the estimate that I get from my procedure does not coincide with the true effect.
Okay.
And so now the only question is, what do I mean by average? And here I mean the arithmetic mean. It turns out that IV is median unbiased, but mean biased.
Okay. And so it simply means that just the mean is biased, basically. Any estimate you get of the mean is biased.
It is biased. No. The estimates that we get on average are biased.
Okay, thanks.
Cool. Thank you for that question. Okay. So here's what's difficult and here's what's not. For the most part, programming instrumental variables in Stata or R really isn't too difficult. We'll go through Stata examples, and I think by the end of this course, you'll agree that Stata makes life comfortable for us. But that's true of many estimators. Statistical software programs have become so good that really I could give Stata to my 11-year-old, and my 11-year-old would be able to press the right buttons to get an IV estimate. But there's no guarantee that that would make any sense, right? So we can press buttons, but the real art here is to figure out when we should press which button. In other words, the real challenge lies in understanding the assumptions that justify estimation, IV estimation, in real applications, right? We only want to press the buttons in Stata when we have reason to do so, when pressing these buttons actually has any hope of giving us a good estimate. So that is what we will spend most of this course about. And my key goals are really to help you first understand the exact nature of the problems that we're trying to solve, right? No tool is useful unless we know what it's good for. And second, we want to know exactly under what conditions we're allowed to use that tool. Now, so that sounds kind of painful, right? So we need to understand the assumptions under which we can use IV. Do we really have to make assumptions? Yes, Yes, we do. Here are some facts. First, it's a fact that all causal inference relies on partially untestable assumptions. This is proved, okay? This is simply a fact. Causal inference relies on partially untestable assumptions because we're comparing potential outcomes across counterfactual scenarios. You can never observe both potential outcomes for any individual, and hence you have to infer the missing potential outcome. That's why it's called causal inference, not causal observation. Okay, and inference is just a fancy word for making stuff up. In a principled fashion, yes, but we are making stuff up. Okay, and we can't pull our potential outcomes out of thin air. We have to deduce them with the help of data and assumptions together. So causal inference always needs assumptions. This is even true in randomized experiments. Right? You remember, randomized experiments are great because they give us comparable treatment and control groups. But they only do that on average in very large samples. For any given randomization, there is no guarantee that your treatment and control group are comparable. And while we can test comparability on a few collected baseline variables, we can never verify comparability with respect to all possible baseline criteria, including the unmeasured and those not even known to science. So yeah, I'm told that in psychology, people call this the assumption of happy randomization. And that's an assumption. All right, good. So that's the fact. Life's hard. Second, the good news is that the more assumptions we make, the easier it gets. If we make enough assumptions about how our data were generated, causal inference becomes an algebra exercise. A difficult algebra exercise, but an algebra exercise nonetheless. Okay, so with enough assumptions, you can just give your data to a computer and the computer will tell you what's what. But you have to make the assumptions. Okay, so should we just make lots of assumptions to make life easy? Well, no, because fact 3 is that, making incorrect assumptions can introduce bias. Therefore, we must carefully justify our assumptions as best possible. And it's justifying these assumptions rather than merely making the assumptions. That's the hard part of science. So my goal in this course is to help us understand the substantive empirical content of these assumptions, right? Because anybody can make assumptions, but we want to be able to make them responsibly and to be in a position to justify them, not just by stating them, but by explaining for our given application why these make sense. Okay, so this course is on IV, and it's on IV, and it's on IV. We'll introduce different flavors of instrumental variables analysis that are going to be distinguished by the assumptions that they make. We will start with a comparatively easier case of really strong assumptions. Indeed, about 2/3 of this course will deal with a world where we assume linearity holds. I don't love this assumption, nor should you, right? But linearity makes learning what's going on much easier than once we've truly grasped that, we can relax. For example, we'll permit effect heterogeneity. So this means that we'll cover the same general ground repeatedly, sort of like a bird that's circling the ground at ever higher levels of abstraction and generality. Now, of course, we can't wait to relax assumptions. We know that making the wrong assumptions can bias our analysis, so we want to make the least onerous assumptions possible. But relaxing assumptions comes at a cost. The fewer assumptions we make, the weaker our conclusions get. In the extreme, if we make no assumptions, we can't say anything about causal inference from data. So let me just preview here a key result. Under the assumption of linearity, which entails constant effects, instrumental variables analysis with met assumptions recovers the average causal treatment effect, or 8 for the entire population. That's great, right? Because that's what we usually want. We want average causal effects. And with linearity and constant effects, you can do that. But if you now recognize or admit that the world's probably not linear and treatment likely has different effects on different people, in other words, if there's effect heterogeneity, then under the best of circumstances, IV estimates the average causal effect only for a latent subgroup of the population, the so-called local average treatment effect, or late. And often, IV will fail to identify any sort of causal effect for anybody. So that'll be the dance that we'll make. Start with strong assumptions in which everything seems possible, and then relax the assumptions to get ever more realistic, but paying the price that the fewer assumptions we make, the less we can say about the world. And then in any given application, we will have to find that sweet spot where we, only make defensible assumptions and hope that we can still recover something about the world doing it. I'll give you lots of examples where people have tried that, and even some examples where the scientific consensus remains that they have succeeded. Good. So throughout, we will mingle theoretical exposition with empirical illustrations and practical exercises. We'll use some Stata. We'll use some pencil and paper. As I've mentioned, we have more slides that we can possibly cover in this course, but that's a good thing. We can prioritize. You can rest assured that I'll make sure that we get through the promised material and that, we'll settle all the key results that I think, are needed for competent applied, high standard instrumental variables analysis. And then I hope that this material will then also enable you to read more specialized literature to, get into the weeds, getting into the higher stratosphere, whichever way you want to call it. Please ask questions anytime. Okay. Let me give you a little bit of history here about the development of instrumental variables analysis. This history will be kind of instructive because this course will roughly travel in parallel with the historical evolution of IV. Turns out that IV has been around for a century. It first appeared in Appendix B of Philip Wright's monumentally boring book called The Tariff on Animal and Vegetable Oil. If you're at a university, check your university library. You're guaranteed to have this book in there. I checked it out. It's painful. But Appendix B is a thing of beauty. Now, people aren't sure if Philip Wright wrote this book, wrote this appendix, because Philip Wright, if I may regale you with the story, Philip Wright was father to Sewell Wright, the famous geneticist and inventor of path analysis. So it stands to reason that Philip got help from his brilliant son Sewell in coming up with this completely new way of extracting information from data. So some people got really serious about this. Stock and I forget the second author, apologize, actually went into forensic linguistics to figure this out. You know, sort of like people do text analysis to figure out if if ancient English plays were written by Shakespeare or Marlowe by comparing word frequencies. So people did that with the tariff on animal and vegetable oil, feeding it word frequencies from Philip's writing and from Sewell's writing. And unfortunately, the evidence is inconclusive. Could have been written by either one. In any case, Philip Wright invents this or publishes this, and then it gets forgotten. Then, in the 1940s, Anderson and Rubin actually invent a technique called limited information maximum likelihood information. These were two like super young mathematicians at Stanford. Rubin taught there until 2 or 3 years ago. Oh, sorry, was it Anderson? I don't know, but like they've been active and key. They invent this technique, limited information maximum likelihood estimation. This is a technique that's super mathematical, very hard to understand, but it is essentially an instrumental variables technique. But you know what? That too got promptly forgotten. Nobody used it because there was no feasible way of estimating standard errors. Then in the 50s, we have the third invention of instrumental variables analysis by Tile, Bassman, and Sargan. They invent two-stage least squares estimation. That's the third approach to estimating, the IV setup. And it's since become synonymous with IV. Okay, so when almost anybody estimates instrumental variables, they really estimate they use the two-stage least squares estimator. By the end of this course, you'll recognize that two-stage least squares is just an estimator that exploits the IV conditions. There are other estimators that can exploit the same conditions, and different estimators have advantages and disadvantages that we'll learn about. Now, okay, in the 70s, Hausmann developed some important tests for the IV assumptions. We'll talk about them. In the 80s, Hansen invented or developed the general method of moment, or GMM. That's a very general estimation approach that also nests an estimator that can be used for the IV conditions. We'll talk about GMM. I think GMM is, generally preferable in most real situations, but it's not typically taught in required courses outside of economics, so very few people use them. That's why we're here. Okay, and then came a period where IV fell out of favor. It fell out of favor because, there's this highly technical liminal and GMM literature, lots of matrices, calculus, projections, stuff that most scientists aren't deeply comfortable with, and that they certainly don't have the training to sort of parse substantively to figure out what on earth this means, right? It's fine for somebody to say that, X prime E needs to be 0, but then we're asking, pray tell, what does that mean in my application? Good. So it fell out of favor. People started to doubt it because it just seemed, the conditions seemed to be really tough. And then along came Angrist, Imbens, and Rubin in a paper in 1996 that is so famous that it has acquired a nickname. It's called Error 96. Ask any applied statistician of observational data analysis or causal inference, they will know what Error 96 refers to. So this paper did two great things. First, it married the old instrumental variables literature with the modern potential outcomes framework to clearly show what type of causal effects IV estimates. And second, in the process, they greatly clarified the meaning of the IV assumptions. And the rest is history. Since then, IVs really become extraordinarily popular, also outside of economics. And Imbens and Angrist won a Nobel Prize, I think, just last year ago. David? Can't hear you. Please turn on the mic. Thank you.
Yeah, you didn't mention here any of the issue discussed before in terms of standard errors being 2 or 3 orders of magnitude higher than they typically be, I guess.
Yep.
Anything I've looked at or done, if the standard error was 2 or 3 orders of magnitude higher, it'd be pretty useless to me on that. Did that come up at all, basically, in any of these or discussions?
Yes. So we will talk about standard errors. The choice between liminal GMM and two-stage least squares will be chiefly driven by the trade-off between, well, no, it's going to be chiefly driven by standard errors. So we'll talk about this. You know, the fact that these standard errors are large is just a fact of life. But if we have the option of choosing between estimators, we'll want to know which ones are more efficient under exactly what situations. And we will talk about this likely on day 2.
Right. Okay. Thank you.
Great. Okay, good. Then in the 1990s, we have a literature on weak instruments. We'll talk about that. Heckman talked about IV with heterogeneous responses. And then also from the 90s, but really from the 2000s onward, computer scientists have gotten interested in instrumental variables analysis, especially the work of Balke and Pearl. And they've contributed some really clever tests and insights that we'll touch upon on day 3. For those of you who have some background in instrumental variables analysis, Balke and Pearl have shown a way to test the exclusion assumption in just identified models, something that still by most people is considered to be impossible, but it is possible, and you'll see exactly how that works. So we organize the material in this course by whether we have a just or over-identified model. Furthermore, we'll organize the material by whether we have treatment effects that are fixed or heterogeneous. Now, a just identified model is just a model in which I have as many instruments as I have endogenous treatments. And an over-identified model is where I have more instruments than endogenous treatments. I'll define all of that, okay? But that's the story. So we're here. We're done with motivation and outline. And now I want to talk about some preliminaries. So the goal of this course is, of course, to convey deep intuition, working knowledge of instrumental variables without appealing to matrix algebra, for which most people don't have applied intuition. I'll give you some matrix expressions, but nothing will rely on that. Instead, I want to develop deep intuition here by working with linear models and using Sewell-Wright's path rules, something that is still used, or that may be familiar to those of you who have a background in structural equation modeling, but is otherwise typically not taught anymore. Now, you'll see that I'm a huge fan of path rules because they allow us to understand extremely deep problems in IV analysis without using matrix algebra. So in this section, we will just cover some useful facts about linear models. I'll settle some terminology. Then I'll notate linear models via graphical path models. And then we'll learn Wright's method of path coefficients to quantify linear associations and to derive causal identification results. Once we're done with that, we're ready to understand exactly how IV works. So I'll use the term model a lot in this course. And when I talk about models, we need to distinguish carefully between data generating models versus statistical models. When I say model, I typically refer to the data generating process, or rather my beliefs about how the data were generated. The data generating process is usually called the DGP. So a model in this sense is a structural model or a causal model. It's, a set of statements that describes how the world works. So let's look at this equation. If I call this equation a model, then I'm claiming that this here is the law, is the process by which the world has generated my outcome y. So this is a super strong claim. Y is generated as a linear function of x1 and x2 and some unobserved factors e. That's a very strong term. I claim to know the functional form here. Yeah. Now, don't confuse the structural model, the DGP, with a statistical model. Now, unfortunately, convention dictates that we also write this thing here for a regression model. And a regression model is often called a statistical model. But OLS is just a tool to recover information about the DGP. The tool to recover information about the DGP is not the same as the DGP itself. So that's why we have to be very careful to distinguish between a structural model, which describes how the world works, and the statistical tools that we use to pry information about the world from our data. Now, most IV applications require linear DGPs. We will deal with nonlinear models as well, but most of IV deals with linear models. So here, this here would be a linear model of the DGP. It's linear in the sense that it's linear in parameters and has constant or homogeneous coefficients. So let's look carefully at this here. We have coefficients B1 and B2, or rather, they're not really coefficients, they're parameters in the data generating process. Notice that the B's here do not have a subscript I. So that means that I believe that the structural parameters, the causal effect of x1 on y and the causal effect of x2 on y, is the same for each individual. So all the bi1 equal the same number b1. That's a very strong notion of a linear model. Now here, by contrast, we have a model that's not linear in the sense, and you kind of got to squint to see the difference, right? The difference is that here I permit that the causal effect of x1 on y differs across individuals I. Now, in the sense that this effect differs across individuals, there's some variance in the structural parameter. We call that effect heterogeneity. Most of IV cannot properly deal with effect heterogeneity. We need very special circumstances for effect heterogeneity to still, permit IV. But we'll talk about those circumstances. So we assume linear DGPs for most of this course. That is to say, for most of this course, we're not just using linear regression type models and its cousins for statistical convenience. Rather, We're actually standing in front of our audience and protest with conviction that we assume that the world is linear with constant parameters. We do that because IV works best in a linear world, and IV accomplishes a lot less in a nonlinear world. So if you really don't believe linearity, then often IV will not work for you. Now, as a notational shortcut, I'll drop the I's in most of what I say. Henceforth, you just have to remember that every model that I write out is linear in this sense. Johannes, please.
Thank you, Felix. Just to make sure, so when you say linearity, you mean linearity in the parameters and not something
Correct.
like variables with powers or interaction effects or something like that?
Correct.
Okay, thank you.
Yes. Here. With linear parameters, that's what I mean. Thank you, Johannes. Oh, sorry, I should say, I think half of this audience is international. I'm going to follow the American convention and just going by first names. And of course, you should feel free to call me Felix. And I hope that's okay with all of you. All right. Now we know what we mean by a linear model. Now, we will represent our linear structural model of the DGP using so-called path diagrams. Path diagrams are essentially, no, not essentially, they are linear versions of the much more general family of directed acyclic graphs. I'm not going to do an introduction to graphs really here because I have a different course on that here at Statistical Horizons, but I'm just going to give you the basics because, like, I kid you not, it's going to be extraordinarily useful. So what's a path model? This is a path model or a DAG. It consists of three things. First, we have these variables, which may be observed or unobserved. Then we have arrows that represent linear direct effects between pairs of variables. And then we have missing arrows. Okay, so for example, there's no arrow from U to T. That the absence of this arrow encodes a so-called exclusion restriction, a sharp assumption about the absence of a direct causal effect for everybody. Okay, so the absence of a direct arrow from U to T means that changing U will not affect T for anybody, for any mechanism other than going through X. So when we work with graphs, we're going to make super strong assumptions. We're going to assume that the graph displays all observed and unobserved common causes of the variables in the graph. Again, when I give you a DGP, I'm going to assume that it is true. Or rather, I'm going to assume not just that it's true, but I'm going to assume that I've told you everything we need to know about it. And what we need to know are common causes, regardless of whether they're observed or unobserved. A common cause is any variable that causes at least two other variables in the system. So the variable U is a common cause of X and Y. The variable X is a common cause of T, C, and Y. Again, I'm assuming that we have all common causes notated, regardless of whether they're observed or not. Let me give you an example. Those who've taken my DAG course will know this example, and I hope you'll forgive the refresher. So here I'm interested in understanding how health behaviors and certain social conditions work together to kill people. So this is a model, social model of mortality. So let's start here. Let T be smoking. I believe that smoking causes cancer. Furthermore, I believe that cancer causes mortality. Why? Now you'll note that there's no arrow directly from T to Y. That means that in my DGP, I believe that smoking causes mortality only via cancer, not via anything else. That's what I claim here. Then maybe we have X, that could be low socioeconomic status or poverty, if you will. We believe that low socioeconomic status causes smoking. So nicotine is a drug, makes life more bearable. So I think smoking, low socioeconomic status also may directly cause cancer. The mechanism here might be exposure to environmental, residential, or workplace toxins. Okay, so poverty causes cancer, even net of smoking. And I believe that poverty has an effect on mortality, even net of smoking and cancer, perhaps because poor people are more likely to become victims of violent crime or to suffer accidents, lethal accidents. Finally, there's an unobserved variable here. Let's call that childhood insults to health. Severe childhood insults to health are believed to cause poverty in adulthood, but they only cause smoking through poverty, and they only cause cancer through poverty and smoking. However, childhood insults to health can also affect mortality later in life through the long reach of childhood. My point of going through this example was that this is actually a pretty complicated story. This is at least a half manuscript page in a medical journal, which prize efficiency. In sociology, this would probably be a 2-page story. And we could capture everything that matters about it causally in this very concise graph. Now, you remember that causal inference relies on causal assumptions. The graph shows you all the causal assumptions that are necessary. It shows you which variables are believed to cause each other and which variables are not believed to cause each other. So which variables have exclusion restrictions. Because all of our inferences are going to be conditional on the truth of this model, the first thing you should do in an applied project is to really interrogate these assumptions and whether they're credible. Here, I don't think this model is particularly great because the model claims that smoking causes mortality only via cancer. Any health scientist will tell you that that's not correct. Smoking can also kill through emphysema, for example. Okay. So if we're convinced of that, then we would actually have to add, oops, no, it's my drawing tool. Then we would have to modify this model to add this arrow. Here. Okay, now these models are one-to-one equivalent to the system of data generating structural equations. In the linear interpretation, which is what Wright used, we can just read the structural equations from the graph. For example, let's look at the equation for C. This graph says that C is caused by all the variables that have an arrow into it. So C is caused by T and X, and by the unobserved stuff, the idiosyncratic error term that affects C. So the linear version of that says, well, C is caused by T and X and E of C. We could take this non-parametric by taking out the functional form stuff here and just noting that C is generated by some function that takes T, X, and EC as inputs. Now, if you really love algebra, by all means, work with these systems of linear equations. If you're really good at matrix algebra, that has real advantages. But for developing applied intuition, I think inspecting these graphs for almost everybody has real benefits. So that's what we'll do. Now, every variable is caused by tons of stuff. We omit so-called uncorrelated error terms from the graph for convenience. Idiosyncratic or uncorrelated error terms contain all of the causes of a variable that are causes of only that one variable. So here, E of C contains all of the unobserved variable that cause only C and not X, T, or Y. The error term on T contains only the variables that directly affect T, but not anything else. And just believe me, you don't have to clutter your graph with these idiosyncratic error terms because they really don't add to identification. Correlated error terms, by contrast, must be drawn. Correlated error terms refer to variables such as U here that are unobserved and cause at least two other variables in the system. Again, correlated error terms refer to omitted variables. Really surprised at how little that fact's known, so perhaps that's new to you, but it's the case. Correlated structural errors refer to unobserved confounding. So they must be drawn, and there are various conventions for that. I prefer just being explicit about the presence of an unobserved common cause. But we could also use a shortcut of drawing a dashed bi-headed arrow, or we could go maximal, and write out the error terms and then notate that some of them share elements. I find this very cumbersome. I usually use these two ways of notating correlated errors.